Everyone, my name is Mohammed Kemal and my fellow Hicham is
Hello
with.
everyone.
All right, so we're going to start presenting the finding that we have in forecasting customer loan default using the assembler learning method. We basically use data from the lending club, which is based in San Francisco. So they basically use the lending match app or application that match different people based on the criteria they collected, and they decide whether to give a loan for them or not, because if they default they're not going to give to them. So here, if you go to the lending match portal, you will see this entry. You can look the personal loan, you can get up to 40,000 with a different criteria based on the information they collected from you. So here is mainly these days you will see different loan application, and then those application they go into the system, which is the algorithm, and the algorithm will decide is it safe to loan or not safe to loan. All right, so we started thinking how we can determine if the consumers are eligible or not, and normally this happen with a common scorecard. So we are trying to use machine learning to determine whether users can be given users can be lending to them or not. So we use the assembler learning, which is a better way that we decided to use. Alright, so here are some of the challenge we have faced. We will in detail explain the challenges in the later upcoming slides. Alright, so the project implementation, we started from cleaning the data, and there are categorical data. We basically applied NA on the data that were missing, and also we use the chi-square analysis to understand if they are MNR or MAR or MCAR. So we're going to explain those also in detail with the slides coming up. So the future engineering, we start creating future based on the existing futures, and then we name that time since the first credit, and we calculated the difference between the loan application date and the first credit line that was opened, and we transform that one into a false category number and transfer the target variable into a binary outcome, which is 0 and 1. So if it came to 0, that user going to be default, and 1 is going to be good. So furthermore, if anything with positive or negative correlation of 75%, and we remove those values based on the chi-square. Alright, so the first thing, we eliminate the future which have only one factors or constant value. We also run multiple random forests to make sure that our data is gonna be very good. And we use the Clara method, which basically used for large data sets, and also we applied Silhouette method, which estimate the number of optimal numbers of the cluster. And when you come to the normalization, we use the Gaussian normalization technique, and also we divided our data into a training and a test set based on the 80-20 principles. So these are the number of machine learning models that we have applied, and we tested which one work very well and which one is not. So we also have that analysis coming up, and Hicham is going to explain that for you guys. So the performance wise, we have a confusion matrix and also the accuracy, and we also have the AUC, which is divided by the ROC. Perfect. So for the result part, I'm gonna give the floor to Hicham, and Hicham, here is your floor.
Thank you very much, Mo. Okay, Mo. So the first thing that we did was to analyze whether the missing data in a data set were correlated with customer loan default, which is what we're trying to forecast. And what we found out is that using chi-square analysis, people that were not putting any employment title into the application were most likely to default. The second thing that we ran was recursive elimination function, and this mainly highlight what are the key feature in a data set. So on this graph, you can see that the top 8 variable have the lowest mean squared error, and this top 8 variable are the loan amount, the annual income, the interest rate, the revolving balance, the time since the first credit, the number of open accounts, the total number of accounts ever opened, and finally the term of the loan. When we run the machine learning model, we got some pretty high accuracy results, both in sample and out of sample. So in our training set, we got KNN with 100% accuracy, and for us just slightly behind with 99.999% accuracy. However, when we look at the test set, you can see that some models are much lower, KNN especially. We're going to come back to it later. Some other models are more or less the same, which can be a good thing, meaning that they perform as well on training data than on test data. But sometimes it's not the good news, and this is what we're going to see in our next slide. So this is our confusion matrix. And 0 means that the customer defaults, and 1 means that the customer doesn't default. When we look at these confusion matrices, we see that most of our model focus on the customer that will not default. And this is because there's a large class dominance, as we were explaining earlier. 85% of the people in our data set did not default. And when we look at, for example, kernel SVM and linear SVM model, they classify all the individuals as non-defaulting, and this is because they were not able to separate the data, and they were just better off just saying that all the customers are not going to default, and this is where the problem. This is the problem with the data set. So the common solution for class dominance is to increase the number of customers that do not default. So we restore class balance. So this is important for further study. What we did also, we use clustering approach because we hope that clustering would help us separate data points which have different features, which will help us calibrate better our model to, for example, to customers that will default. The output was not great, meaning that it didn't improve the model, it didn't make it worse as well. So we just leave it there, but at the end, it was an interesting study to do. Now we're going to compare slightly all the different models, and we'll do one that are comparable. For example, we have KNN versus naive Bayes. So KNN and naive Bayes are very close algorithms that classify a point by looking at the class of the surrounding point. KNN usually performs poorly when there is class dominance. And we can see that by looking at the out-of-sample accuracy of KNN, which is only 76% compared to 100% on the test, on the training data. While the naive Bayes is performing moderately well with an 82.6% accuracy. Now we're going to talk about the SVM, which is the kernel SVM. So the linear SVM has coefficients that are very, very close to 0. What it means is that the linear SVM was not able to linearly separate the data. So it couldn't put any factor in. When we look at the kernel SVM coefficient, we can see that we have very high annual income value, which means that the higher the annual income, the lower the customer default. In contrary, we had, for example, the higher the loan amount, the most likely the customer will default. So annual income was positively correlated with non-customer default. Why? Okay, I will stop here and